welcome to the course Advanced Reaction Engineering. Today we will discuss about non-ideal flow. If we want to conduct any reaction, so then we have to choose the reactant, so and we have to fix the reactions, and after that we have to choose any reactor. So there are many reactors: batch reactor, plug flow reactor, CST reactor, bubble column reactor, slurry reactors. Many reactors we have studied, so we know. And now question is, means the reactors we design or exist, that is real reactors. So real reactors has many problems, means once we design the reactors, many way you can design the reactors. So for our to purpose the reactions. Okay. So once we have that particular reactor, so reactants once we charged, so reactants go inside of the reactor through the inlet of the reactors. Once we it is passed inside of the reactor, so if it is small reactors it is fine. So but when it is industrial scale large reactors is there, and so large quantity of the reactant that is feeding through that feed inlet, and if it is one component or multiple components of the reactants are there, so then their distributions, means how they are flowing inside of the reactor, that is very important. Means the nature of the reactants once it is enter inside of the reactor, so how they are behaving there. So means how long, means if we know the volume of the reactors, volumetric flow rate, that is the fixed, so then residence times or space time, that is the tau, that is the fixed for all component whatever it is entering in the reactor. But if let us say the reactions is A is going to A plus B, A going to this C plus D, means here reactant A and B is there. So the once these two reactants come in contact, then only reactions will proceed. So mixing is very important in between two, and if reactant is passing through these reactors, let us say A is going, B is also going, but A is taking less times, it is leaving from the reactors, but B is present there. So B will not interact with the A. So then there would be reactions would be, means there is no possibility of reaction. So they both come in contact in the right environment, means temperature, pressure, catalyst contact. So then their reactions would be proceed. So means somehow some anomaly is there once it is entered. So sometimes we get low concentration, low conversions, sometimes we get high conversions, means fluctuation is there. So that is due to the distribution or residence time distribution or the times they spend inside of the reactor. Maybe reactant to reactants are different, that may be due to the fault of the reactors that we have designed. So that nature, means up to, means always whatever the reactors we designed or we fabricated, that is real reactor. So how the real reactors is deviated from the ideal reactors, when non-ideal is coming from with that ideal also is coming. Non-ideal means that is the real reactor that is does exist, and ideal that is not exist, means whatever the reactors that we develop or design fabricate, that should be close to ideal. If it is far away from the ideal, that is not acceptable from the industrial point of view for the reaction if you want to conduct. So therefore always that should be close to ideals, not exactly ideal is not possible perfect reactor. So close to reactor ideals, the reactors we can develop. Okay. So these are the things, means residence time distributions already have studied, again so we will study it here, and in the few lectures we will get an idea about various type of models, theoretical models have been developed. So that we will discuss. Okay. So these are the reactors we know. So this is the plug flow reactors, this is the backbed reactor, this is CST reactor. So these are very common reactors. In this particular reactors, non-ideal flow natures we will discuss, that means residence time distributions we will discuss. Okay. So in this particulars, means the reactors we have to want to means study, want to characterize that particular reactors, what are the deviation is there, so up to what extent it is deviated from the ideal. So that we want to check, means whether the reactors we have designed is perfect or not, that is suitable for that particular reactions or not. So then to characterize this non-ideal nature of the reactors, so ET we have to know, TM is we have to know, FT and sigma square, that the things we have to find out. So what are these components? We already have studied in UG courses, again we are repeating here, it is the residence time distribution functions of that particular components or reactants that we are feeding inside of the reactor. That functions, residence time distribution functions, we have to find out for the reactor. We have to check that, we have to test that. Tm is the mean residence time that component is present or passing through these reactors. The mean residence times of individual component or the reactants we have to know, cumulative residence time distribution function, and sigma square, that is the variance we have to know. So, means the to characterize this reactor, basically our reactors is of norm from an ideal reactors. So, by this way we can find out, and second is once we know these are the components. So, using those components we can find out, means predict, we can predict the conversions and exit concentration, means once we have a, let us say these reactors we have. So, here we are conducting any reactions, A is coming here. So, if it is 10 milliliter volume of the reactors, very small volume of the reactor, V equals to 10 milliliter. So, here conversions means Ca initially let us say 100 mole per dmq we have given charged, and at the end of the reactions let us say 10 mole per dmq we are getting. Okay. So, small reactor, small quantity of the reactants we can pass here, easily we can measure, we can characterize these reactors, quantify we can do. But when large scale reactor is there, so here volume was 10 mLs, here volume let us say 1000 liters. So, if we check these reactors, means then we have to conduct the reactions. So, but if this reactant is very costly, let us say 1000 rupees per gram, let us say, or per kg. So, very costly. So, too much means reactant you have to pass to check that things, but this is sometimes is not possible. So, means to the reactors for industry we have designed, we have to check that. So, for this is the basic purpose of this RTD study or residence time distribution study. Okay. So, by considering instead of reactant, so we can put something inert materials. So, by that we can check that will come discuss later. So, here's the residence time distributions why it is required. So, to predict the conversions of a non-ideal reactor. So, that we basically discuss here, and then we go for that. So, okay, let us say gas liquid reactor contactor is there, or slurry type reactors or other type of reactors is there. So, in that case two phases are there, reactant is A is the gas and liquid component A is the gas and B is the liquid. So, these are the reactants. So, B is passing from the top and A is passing from the entering from the bottom of the reactor in the form of bubbles, gas bubbles. So, A is leaving this way and B is coming after reaction this way, and product formation is there, C is with B, C, if C is the liquid then both will come from the downs. So, here's bubble formation, C is bubbles, and here's the interface A and B is there, gas and liquids, their reactions will take place. Okay. So, here's the residence time distributions why it is important. So, here the bubbles that is coming from the bottom to the top. So, it resides different times inside of the reactors, its size also is different, bubbles diameters may be smaller, larger, different type of there. So, therefore, the interactions are in contact, interface contact in the bubbles would be different. Therefore, overall conversions distributions would be different, concentration that is the coming out, exit concentration, here exit concentration of the B is coming different, and that would be different, means actual how they are behaving inside of the reactor. So, why there are changes that if you want to know. So, then this RTD study you have to do to check the reactors. So, to understand the residence time distribution and their effect of the chemical reactor performance we need. Similarly, for packed bed reactor is also, this is the packing material is there. In the packed bed reactors we usually put solid catalyst here, and then reactant is passing A would pass through this bed, catalyst bed is there. Okay. So, when reactant is flowing here, means some void spaces are there, are some molecules without interacting with the catalyst surface, they are leaving from the reactors. It takes very less time. If there are some molecules spends longer period of time, so they are not getting space to leave from the reactors. So, remain there inside, means accumulation should be there. So, and few interacted with that catalyst surface and leaving from the reactors after reaction. So, then these are the things of the packed bed reactor. So, this type of means when reactants leaving without interacting with the catalyst surface, if it does not interact with the catalyst surface, there would be no reactions. Therefore, this type of things means without interacting is called channel, okay, channeling it is called, okay, without reactions or reactings with the surface of the catalyst it is leaving. So, this is called channeling, and means once reactant Ca 0 is there, here is Ca. So, without reacting, if reactant pass through the reactor, then conversion should be low, okay, means all the reactant does not take part in the reactions. So, few molecules take part in the reaction. So, therefore, that is not acceptable when we design a packed bed reactor. So, we expect that all the reactants should pass through the catalyst bed, interact with the catalyst, take part in the reactions, and then it would leave from the reactors. Okay. But in real case or the real reactor, that is not happen. So, sometimes channeling is there, sometimes accumulations is there, then overall performance of the reactor should be different. So, this is the channeling. So, it leaves before the times. So, then what kind of concentrations or if channeling is there. So, it is the called C curves. What is the called C curves, that you already have studied, and C curves, if reactor we have designed perfectly packed bed reactor. So, then this type of natures of the concentrations means reactants, if we pass let us say Ca concentrations, it would be 0 in the initially, and then it would go maximum and then decrease, and then all the molecules leave from the reactors with the different times. So, similarly, if channeling is there, so then suddenly few molecules will come out, and then again it reach to the 0 or down, and then again reach to this. So, in addition, this is the natural and this is also expected. So, but this is coming. So, this type of bump is coming, that is or maybe different type of also may be coming this type of. So, this type of bump is due to this type of channeling. So, very fast the before means maximum times or Tm is the maximum times maybe up to this 0 to let us say 10 minutes, but 0 to 2 minutes few molecules are coming, here also 10 minutes or maybe 12 minutes whatever. So, before time that molecules is coming or coming out from the reactors. So, these are the things means we can study. So, that we will discuss later. So, similarly continuous start tank reactor is also there, in that case also reactant is passing here. So, if outlet we fixed here, so then reactant molecules without mixings or taking part longer period of time, it may leave from the reactor. This is called bypassing, means here a particular space is there, within that reactant molecules spent, that maybe you are expecting whatever the molecules is entering 1 hour that should spend inside of the reactors, but few molecules following this pathway it is leaving in after 30 minutes. So, this is called staying very less time. So, then conversions yield selectivity would be different, and few molecules at this particular space remaining for longer time does not take part in the reactions. This is called dead zone. So, instead of 1 hours they remain inside of the reactor 1.3 hours. So, then overall performance Ca and Ca naught. So, based on that we can get Ca naught minus Ca by Ca naught. Okay. So, here Ca is different, concentration would be different due to this. So, therefore, some performance or conversions of the reactors would be different. So, if you unable to design the reactor not perfectly, want to design the reactor perfectly, but if it is not possible, in that case this type of problems may appear and we have to address those things. Okay. So, then residence time distribution functions, that is RTD. So, it is important. So, we have batch reactors, we have a plug flow reactors. In batch reactors, so let us say all these are the reactant molecules we put inside of the reactors and spend 30 minutes, and after that we collect all molecules together. Then batch reactors, all atoms or materials within the reactors have been inside having identical length of times, that is 30 minutes, let us say T equals to 30 I said. So, all molecules spending same times. So, then batch reactor is an ideal reactors. Similarly, plug flow reactors, all atoms of materials leaving the reactor have been inside for the same exactly same amount of the time. See here, if there is no bypassing, no dead zone is there. So, all molecules, let us say this molecule, this is entering here and this move like this. So, all molecules whatever living along the x axis. So, it is moving out from the reactor spending equal time. So, then it would be also an ideal reactors. So, all molecules if spend equal residence times. So, thence it is an ideals. In case of the CSTR reactors also we are expecting here mixing is there, residence times or the time all molecules spend should be equal, then that also reactor should be ideals, but in real case it is not possible, some anomaly or differences we can observe. So, this type of reactors is called non-ideal reactors. So, in that particular reactors residence time distributions will study. Okay. So, for this type reactors residence time distribution function is important. So, residence time distributions what actually give us, if RTD of a reactors if we find out, so then it actually gives us the mixing property of that reactant. So, I said reactant A and reactant B, if we do the same these reactions, if component A remain few left here, component B is leaving this way. So, B is spending less times bypassing. So, then exact ratio will not maintains since mixing is not proper. So, then due to the non-ideal nature of the reactor, if we exit that make here, so then would be different nature from this exit. This is the outlet of the reactors. Okay. So, from actually this residence time distribution functions if you are able to find out, so you can get an idea means whether the reactants entering, so mixing is proper or not. So, then by for that so we can change the design or somehow mixing or stirring that we can change, we can put more stirrer or somehow the some other way you can change or think about the reactor. So, why it is not getting higher conversions, why we are getting the reactant take spending the reactors very less times. So, these are the things we can find out. Okay. So, to measure the RTD or residence time distribution functions experimentally how we can conduct. So, we have to inject some instead of reactants, I said the reactants may be very costly. So, then we cannot use that to find out the RTD, or we can not characterize the reactors by using direct reactants, so that reactions will conduct. So, for that we have to use some treasures. Okay, treasure materials we have to use, that may be any chemicals very less costly, less price is very low. So, molecules we can use atoms, radioactive materials, dye we can use that is not corrosive if it is or NaOH whatever. These are the materials we can use, or some other things are also available, inert materials that we can use for the reactors means and find out the concentrations once it is leaving from the reactor. So, these are the component is called treasure, and the trace is called treasures is okay, or any color radioactive materials also we can used. And the method of suppose we have these reactors, here we can inject. Okay. So, here this is the feed line, normal solvent is moving, and here treasure we can inject here, that injections may be pulse or may be step inputs. So, maybe let us say like infusion of injections in our body 1 ml, 0.5 ml, very small quantity we inject or infuse in our body, like that. Treasure also we can infuse. This is the system. So, here you can say this is the feed lines, the reactant or any solvent, let us say water is moving, and here treasure is the dye, a very small quantity 10 ml we can inject. Here it has a particular flow rate 10 milliliter per minute. Okay, let us say it is flowing at this particular volumetric flow rate. So, from here treasures or this dye will pass through these reactors, and then we can collect the sample effluent samples and measures the concentration of the dye at particular times. So, like that at different time the concentrations of the dye we can measure, okay, like that. These are the concentrations we can measure from here exit, and by that if we plot this type of curve will come. This is called C curve, okay. That already you have studied, again you are discussing this type of tracer test we can conduct, and we can get the concentrations means changes after coming out the tracer or reactants from the outside of the reactors 0 to T times. So, what would be the concentration? So, concentrations would vary. This is the tracer or dye concentration, dry or tracer concentrations. Okay. These are this is the maximum concentration, this is the minimum concentration. So, at the beginning it was the minimum, and then it is gradually increase and then drops. Okay. So, this way you can find out. So, now how to get these equations means on to develop. So, let us say very small time delta t, small delta t very small time. So, and concentration of the tracer from the exit, if you want to measure t time and t plus delta t time within that. So, means tracers 10 ml we have injected, 10 ml N0 equals to let us say 10 ml that we have injected. Okay. So, if you do not know how much quantity you have injected, that also from this graph also we can find out. Okay. So, let us say this is known quantity, this is the after delta t times we are getting that molecules, that is 10 ml it was injected, delta n amount, N0 amount it was injected, and we are getting delta n amount at particular delta t times. Similarly, at different times we can get the amount of the tracer leaving from the reactors T and T plus delta T times equals to this. So, for that delta n is the fraction of N0. Okay. So, delta n amounts that may be delta n may be let us say 0.5 ml, at delta T may be 10 minutes we are getting, delta T equals to 10 minutes. So, this is the concentrations we can measure at that particular time. This is the N0, that is the delta n amount of the quantity of the material in terms of milliliter, grams or kg we can find out. This is the volumetric flow rates we know. So, then delta n equals to the amount of the material, that is equals to Ct equals to mole per dmq. Volumetric flow rate is as unit, dmq per unit time minutes let us say, into delta T equals to minutes. So, we can that amount of the moles leaving from the reactor. So, we can easily find out, okay, using this equation 1. Now, if we divided these equations both side, left side and right hand side, equation 1 if we divide with N0, N0 is the initially the amount we have taken 10 ml, and after particular times. So, let us say 0.5 ml or in terms of kg at 0.5 or 5 minutes we are getting delta T equals to 5 minutes, okay, intervals we are getting. So, if we divided left hand side N0, right hand side also N0. So, then we will get N0 in delta n by N0 is the fraction of material that lives in the reactor within these times, okay, T and T plus delta T within this delta T fraction times that is living. So, here this equation, this component part is called ET, it is a residence time distribution functions RTD, okay, small v that is the volumetric flow rate concentration, and N0 is the total amount of the tracer that is injected. Okay. So, now equation 2 we can write this way, delta n by N0 equals to ET into delta T, that is the equation 4. Okay. So, now ET is defined. So, here ET is the resident time distribution function. So, how much time different fluid elements have been spent inside of the reactor. So, ET, that is the resident time distribution function. So, what does it signifies? It indicate actually the how much time it is spent, means we have 10 ml injected. So, in 10 ml all molecules if it is spent equal times, then that is very good. If it is not, if all molecules does not spend equal residence time inside of the reactor, then nature would be different. So, from that we can get. So, ET has units, that is time inverse. If you multiply it with the time, that is the fraction of material that is living within that stipulated time T and T plus dt within that reactors. Okay. So, this is the injection, this is the concentration of the tracer or dye that we have taken, and so this is the 0, means ideally means infusion. So, whenever concentration of the tracer, so 0 times, so means minus tau plus tau, let us say this. So, actually this time is this, means concentrations whenever we inject inside of our body any injection. So, then it should take fraction of times less than very low times, fraction of times means less than 0 second, that should be, but this is the ideal. But in real case, this is the real, means injections or pulse injection, that whatever we do it takes some times, means 1 second maybe, if we infuse anything in our body or this fluid system. So, injections it takes some times. So, ideally it should be a lines, but in real case it should be like this. Okay. So, sudden jump of concentration of reactants or tracer, that is injecting inside of the reactor. So, here initially is when there was no tracer infusion, it was 0, when suddenly injected the tracer inside of that line. So, sudden jump of the concentration should be this, means initially it was 0, sudden jump. Okay. And after that distribution of the tracer should be here, that spends inside of the reactors and then it leaves. So, if we know this, then concentration versus times we can plot, and it would be like this. Okay. This is the pulse response, this is pulse injections and this is pulse response, this is pulse injection, this is pulse response. So, from the pulse response we can get C curves. Okay. So, now N0 is known, if it is known it is very good, if it is not known also we can find out using some equations. So, now equations once was in terms of this equation 1, this was the equation 1, this was in terms of differential forms. So, delta form. So, now if we express in terms of differential, okay, differential forms, so this equation once we can write this, means delta n was there equals to V C t into delta t was there. So, we are expressing this equation in terms of differential form. Now, if we integrate 0 to infinite times, okay, so then in the left hand side dn 0 to infinite, if we integrate that would be equals to n 0. Okay. So, in the right hand side integration is there V C t dt. So, equation 6. So, if we concentrations and time C curves is there, if we integrate and find out the area, total area, that is this. Okay. So, now volumetric flow rate. So, E t equals to V C t by n 0. Okay. N 0 is this. So, n 0 equals to this, from this equation 1 or these equations after integrations 0 to infinite time, the infinite times may be total stipulated times, that may be 1 or 2 hours required to come out all the reactants from that reactors or all the tracer from the reactor. So, that way we can find out the total n 0 amount of the tracer that was injected. So, okay. So, by integration C t is known, V 0 is the constant, if V 0 is the constant. So, if we know, so then say n 0 value we can find out. Okay. So, now volumetric flow rate is usually constant, V equals to V 0. Okay. So, that now E t equals to this. Okay. If V 0 is constant, V equals to V 0. So, then n 0 we can write V 0, 0 to infinite C t dt we can write. Okay. So, now this n 0 if I substitute here, so V equals to V 0 C t by n 0. So, n 0 substituting here, V 0 we have. So, after simplifications we can get this E t equals to this way, C t by 0 to infinite C t dt, this way we can express. Okay. So, this area under the curves we can get. So, means from the experiment C t concentration at different times we can find out, and once we know, then this C t value we can put it here and E t value we have to find out. So, we have to integrate this, means from the C curve this part we can get. Okay. So, then we have to divide C t with this, then we will get E t. Okay. So, this way we can individual times, means 0 means t equals to 0, 1, 2, 3 concentration from the experiment we can get, corresponding E t value also we can find out. So, once we know, then E t and t if we plot, then E curves will get. So, how to get E curves, that we know, how to get C curves, that we know. So, if we times concentration of the effluent concentrations we can know, then if we plot, then C curves we can get, and E curves how to find out. So, similarly if you know, then E curves also we can get, okay, C curves, E curves. And see here at any times within that t equals to, if total time is 0 to 20. So, if let us say within that stipulated times how much fraction of material leaving 5 minutes to 7 minutes. So, then T1 equals to 5, T2 equals to 7 minutes. So, if you know ET dt, so then that way fraction of material leaving within that 5 to 7 minutes, that easily we can find out using this integration procedure, or this way if you know the ET value. Okay. So, total 0 to infinite ET, that would be 1, means 1, why it is coming, this is equals to n0 by n. So, n0 by n0. So, therefore, it is coming 1. So, n0 actually the fraction of materials that is leaving n by n0. So, n1 plus n2 plus n3 plus like that it is coming, n0 by n0 is this, n0 is this n1 plus n2 summation of these molecules that is leaving at this particular point. If we sum up, then total summation of molecules that was injected, that will get, therefore, it is coming 1. Okay. So, thank you. So, today up to this means what we have studied so far, means how to means different reactors, what are the different problems, what is called ideal reactors, what is called non-ideal reactors, and how to find out the what is called residence time distribution functions, and how to find C curves, how to get E curves, okay, how to find out fraction of materials within a particular stipulated times in that reactor, so that we can find out. And suppose if n0 is not known, so then the unknowns quantity n0 also we can find out by this way also. These are the equations we have studied, that would be useful for our next study. I think you already have studied these are the things. So, again we are summarizing or discussing or repeating these things. So, you have to study it. Okay. So, thank you. So, today is up to this.